So our job in this example is to calculate the power associated with each of the three resistors. Now obviously in order to calculate the power, we're going to need to calculate the voltage, we're going to need to calculate the current. The currents, happily, are already labeled in the circuit. So we have I1 flowing downward, we have I2 flowing downward, but that also means, of course, that I2 is flowing to the right through this 2 ohm resistor. So there's really only two currents that we're going to need to calculate. Now we could solve the problem in a number of different ways, but what I'm going to do is I'm just going to make a note of the fact that I2 flows through both the 2 ohm resistor and the 3 ohm resistor, so we could just briefly redraw the circuit. Probably wouldn't need to do this if you were solving this problem on your own, but I'm just trying to make it as clear as possible. So I'm going to redraw the circuit. Having combined those two resistors in series, I'll have 5 ohms as the combination of those two resistors, and then I'll have 10 ohms as the other branch, and then I'll have 8 ohms, and we have I1 flowing down here, and we have I2 flowing down here, and my goodness, it couldn't be a more textbook example of current division. Let's go ahead and calculate I1 and I2. I1 then is going to be the total current multiplied by the resistance in the other branch, so that's going to be 5 ohms, divided by the sum of the two resistances, which is 5 ohms plus 10 ohms, and that turns out to be 2.667 amps. And then I2 is 8 amps multiplied by the resistance in the other branch divided by the sum of the two resistances, and that works out to be 5.333 amps. Two things to check. Do those two numbers add up to 8? And yes, they do. And does the larger resistor get less current? And yes, it does. So those, while we aren't certain that that's a correct answer, we're pretty confident that means that it's a correct answer. So we now know the currents, I1 and I2. We can go back up to the original circuit diagram and say, oh, I'm going to go ahead and label, this as V sub 10 ohms, and I'm going to label that as plus to minus. I'm going to have V sub 3 ohms, plus to minus, then I'm going to have V sub 2 ohms plus to minus. And I can calculate those voltages just using Ohm's law. I notice that I've drawn the polarity of each of those voltages such that the current head, the arrow head of the current is flowing into the positive terminal. So they're already going to be calculating power absorbed. We know that resistors can only absorb power, so that's good. So I'm going to calculate V sub 10 ohms. V sub 10 ohms is going to be 10 times I1, which is 26.67 volts. So just as a reminder, we had I1 right here. It's flowing downward through a 10 ohm resistor. So this is 10 ohms times I1. 10 times I1, which was 2.667 amps, gives us 26.67 volts. We can calculate V sub 2 ohms. V sub 2 ohms is going to be 2 ohms multiplied by I2, which it turns out is 10.667 volts. And then V sub 3 ohms is going to be 3 ohms times I2, which is 16 volts. We can then go to calculating the power. So the power in the 10 ohm resistor is going to be 2.667 amps multiplied by 26.67 volts, which is 71.1 watts. So that resistor is absorbing about 70 watts. The 2 ohm resistor is going to have 10.667 volts multiplied by 5.333 amps, and that works out to be 56.9 watts. So about 50 or 60 watts. And then the 3 ohm resistor is going to be the product of 16 volts multiplied by 5.333 amps, which works out to be 85.3 watts. Now there's more that we can do with power, but for now we've done what we were asked to do. We've calculated the power associated with each of the three resistors. We found that they're 71.1, 56.9, and 85.3, and we'll move on to doing more in the next example.